Chapter 5. In Chapter 5, we deal with the concept of temperature and heat. There is a relationship between temperature and heat, and also related to the motion of the molecules that form the core of these substances that we deal with. On loose basis, we can say temperature is a measure of the degree of hotness or coldness. But to be more precise, we realize that if you heat a substance, the molecules will undergo motion. And so if we can measure the average kinetic energy of these molecules, we will be measuring temperature. So temperature is defined as a measure of the average kinetic energy of the molecules. There are several thermometric properties that change with a change in temperature that can be used to measure temperature as thermometers. For example, a bimetallic strip undergoes an equal expansion, and hence you can make what is called a bimetallic thermometer. Temperature is measured using three scales. We have the Celsius scale, the Kelvin scale, and the Fahrenheit scale. These are based on two fixed points of water. We have the freezing point and the boiling point. On a Celsius scale, the freezing point is 0 degrees Celsius, and the boiling point is 100 degrees Celsius. On a Fahrenheit scale, this corresponds to 32 degrees Fahrenheit and 212 degrees Fahrenheit. And we are going to see how we can convert from one scale to another using these scales. The conversion factors that are used are really very simple. So to convert from Fahrenheit to Celsius, we can use this first formula here, which is 1.8 times the temperature in Celsius plus 32 will give us a temperature in Fahrenheit. If we have a temperature in Fahrenheit, want to change to Celsius, we can take that temperature in Fahrenheit, subtract the 32, which is the freezing point, divide that by 1.8, or use the formula that you see to the right. And the temperature in Kelvin has the same division as the temperature in Celsius, but it goes from 273 to 373. So the conversion again is very simple. You simply take the temperature in Celsius plus 273 to convert to Kelvin, or take the temperature in Kelvin, subtract 273, and you have a temperature in Celsius. By the way, the Kelvin scale is the standard scientific scale. So when we think of temperature in science, we think of Kelvin. You see, especially when we discuss property of gases that it is important that we always use Kelvin to solve our problem. How about the heat? Well, heat is the energy transfer that occurs between two objects because of the temperature difference. And so if I have two objects and there is a temperature difference, there will be a flow of heat. So heat is a form of energy. In the SI system of units, therefore, it is measured in units of joules. But as we'll see, it's measured in several other units that we'll discuss shortly. So, here is what we say. What's the difference? Well, temperature, we said, is a measure of hotness or coldness of an object, and it's actually a measure of the average kinetic energy of the molecules, whereas heat depends on the internal energy. It's a form of energy of the molecules, and we say heat is transferred whenever there is a temperature difference. So here are the units of heat. The first unit that we use for heat is called a calorie. A calorie is the energy required to raise the temperature of 1 gram of pure water by 1 degree Celsius. So it is based on this substance called water. If we define a kilocalorie, which would be 1,000 calories, the definition is similar, except now we look at 1 kilogram of water. If we are using the British system or the English system or the US customary system of units, then there we use a BTU. A BTU is the energy that is required to raise 1 pound of water by 1 degree Celsius. And remember what I said, is the unit of heat is joules, and here is the conversion factor from calories to joules. Now, various substances respond differently when they are subjected to a temperature change. And several factors will affect this: the mass of the substance, the type of material that you are subjecting to a temperature change will yield different amounts of heat. And we already defined a measure of how we measure temperature, and we say we measure it in calories. But here we are talking about the specific heat. The specific heat is the energy required to raise the temperature of a substance by 1 degree Celsius. Note the difference between this and the calorie. Here is the temperature of a substance, and it could be any substance, and different materials respond differently when they are subjected to heat. The symbol that is used to represent this is C. So C stands for specific heat. The units that are used are either calories per gram per degree Celsius, or kilocalorie per kilogram, or kilocalorie per kilogram per degree Celsius. We can also use joules per kilogram per degree Celsius. The fundamental equation that we use to calculate heat is that heat depends on the mass of the substance, the type of material we are doing it. So this is like an intrinsic property that depends on the material times the change in temperature. So this is the quantity of heat, and we'll try to use it in several problems. And so here are the specific heats of the most common substances. Look that for water, which we deal with mostly, in this unit of kilocalories per kilogram per degree Celsius, the specific heat is simply equal to 1. Sometimes people say specific heat capacity, so it's simply equal to 1. Compare that to the specific heat of ice, which is actually about 0.5. So we have already stated that heat is a form of energy that occurs whenever there is a temperature difference. This can occur in 3 ways. The first that is shown here is conduction. Conduction involves the transfer of heat through the collision of molecules. So this is collisions of molecules. So, for example, if you have a bar and you heat one end of that bar, you apply heat to it, what will happen is this will undergo motion, and as they motion, they will vibrate, and they will be transferring heat to adjacent molecule, and heat will transfer in that form, and we refer to that as convection. Not the molecules themselves, they just vibrate at a fixed point, but they pass on the heat to other molecules. Convection, on the other hand, involves mass movement. So this involves mass movement, and we say it tends to form what are called convectional currents. So here is the example. If I have an object, and let's say this is a tank and it's filled with water, so I have water here, and I heat this substance, so I supply some heat. What will happen as the water is heated, it expands. And as it expands, it becomes lighter. And as it becomes lighter, it rises to the top. The cold water, which is at the top, flows back to the bottom. So we form what are called convectional currents. But note, the water itself that has been heated moves, carrying the heat with it. And so it involves an actual movement of mass. The last is radiation. Radiation is how we get our energy from the sun. This goes through a process of where electric, magnetic fields generate electric and magnetic fields generate these waves, and the waves move from one location to the other. And this doesn't require any medium because they are self-generating. Note, the natural flow of temperature is always from higher to cooler regions. Okay, there are 4 states of matter that we talk about in this chapter. We actually will stick to 3 of those 4. That is, matter can exist as a solid, matter can exist as a liquid, matter can exist as a gas. And the fourth state of matter is matter can exist as plasma. In this chart here, we look at 3 of those 4 states. So if you have a chunk of ice, so let's say I have a chunk of ice, which is a solid, and I heat this chunk of ice, so you supply heat to the chunk of ice. What will happen is that the temperature will rise. It will rise until you reach the melting point, which is 0 degrees Celsius. And the amount of heat that you supply from that equation, I'll call it H1, this will be the mass of the ice times the specific heat capacity of the ice times the change in temperature from, let's say, minus 6 degrees Celsius to 0 degrees Celsius. Once you reach the plateau of where it starts to melt, there will be no change in temperature. Because there is no change in temperature, this is referred to as latent heat. Latent implies hidden. So we say there will be hidden heat. Because all the heat that is supplied goes to melting or changing the phase from the solid to the liquid phase. So here, note the temperature at 0 degrees remains constant until all the ice has melted. Once the ice has melted, now turned into water, the temperature will rise again until we reach another plateau. So the amount of heat that we may supply here, I'll call it H2, will be the mass of the ice now become water, times the specific heat capacity of water, times the change in temperature. Let me call this delta T2, delta T1, so that we realize they are not the same. Remember, this was from minus 6 to 0. This is from 0 to 100 or to whatever temperature you want to calculate the heat. Once you reach the plateau of 100 degrees Celsius, we realize again that the thermometer does not change or remains constant. And again, we reach another plateau of latent heat, and this will be called latent heat of vaporization. The area 1 at 0 degrees is called latent heat of fusion. So note again, the heat is hidden because it's going to changing of the phase, and since it's changing the water molecule to the vapor molecule, it's not reflected in the rise into thermometer. When all the water has changed into the vapor phase, the temperature will start rising again until we reach what is called a plasma state. And as I said, we are only going to look at 3 states of matter: solid, liquid, and this here is gas. And this is liquid. So during a phase change, as we have said, we do not see the change in temperature. So the heat is hidden, and because it's hidden, we call it latent heat. If we want to calculate that heat, we find the latent heat is simply equal to the mass of the substance, like ice or water, times the latent heat of fusion or vaporization, depending on where you are. So this is the formula for calculating latent heat. We'll see how we apply this when we look at specific questions. So here is what happens. If we are moving from a solid to a liquid, we say the solid is fusing or undergoes fusion into the changing from a solid form to a liquid form. We say it is actually melting. So it undergoes melting. On the other portion, we say actually it is undergoing freezing if it's moving from a liquid to a solid. So we have the melting point, which is exactly the same as the freezing point. It just depends on the direction in which you are going. Similarly, if it's changing from a liquid to a gas, we can say we have a boiling point. Or on the other end, if it's changing from a gas to a liquid, we can say it is undergoing condensation. There is also a state where we bypass the liquid phase. The object moves straight from the solid to a gas, and we refer to that as sublimation. So we are now going to look a little bit at gases. We have already deduced that whenever a substance is heated, we have these molecules that undergo various motions. And we already deduced that the measure of the average kinetic energy of these molecules is what we refer to as a measure of temperature. So in this, we are going to look at several gas laws. And this will start by defining what pressure is. Pressure is force per unit area. It's measured in units called Newton per meter squared or pascals. Now, it's also measured in other units like atmospheres or inches of mercury, but we are going to stick mostly to the unit of Pascal because that is a scientific unit. So pressure is force over area. And what we'll be looking at here, we'll be looking at the ideal gas law, which in this case, what we look at is we are assuming that the number of molecules is constant, and then we are going to look at the variations of each of these quantities with respect to the other. The easiest way to look at this is to keep one of those variables constant. So for example, if temperature is kept constant, so temperature is constant, what we will have a relationship between pressure and volume. And what it will say is that the ratio of the pressures there is equal to the ratio of the volumes. P2 is pressure at a later stage, and P1 is the pressure at the initial stage. This is usually written as P2 V2 is equal to P1 V1, and this is referred to as Boyle's law. So if we keep the temperature constant, we find that there is a definite relationship between the pressure and the volume. The pressure varies inversely proportional to the volume. What if we keep if the volume is kept constant? Now, what we'll have will be a relationship between the pressure and the temperature. Note in this case, what we note is that the higher the temperature, the higher the pressure. And finally, if we keep the pressure constant, what we have will be that there is a relationship between the volumes and the temperatures. So we have what is called Boyer's law, we have what is called Charles's law, and we have what is called Gay-Lussac's law. So, but all you need to remember is these ratios, and they will always be given to you. So that is it for chapter 5, and we are going to look at a few problems.